I want to do a couple examples of related rates problems with you. So let's get into it. So here we have our first one. A person 6 feet tall stands 10 feet away from the point directly beneath a lantern hanging 30 feet above the ground. The lantern starts to fall, thus causing the length of the person's shadow to change. Given that the lantern falls the distance 16 feet squared in t seconds, how fast will the length of the shadow change after it's been falling for 1 second, or when t equals 1, right? So with related rates problems, the first thing we want to do is start with a drawing. So let's start with drawing the situation. So we have our little person here, and he's 6 feet tall. So we're going to write 6 there. And we know he stands 10 feet away from, that's a little long, 10 feet away from a lantern, right? So 10. And the lantern at t equals 0 is 30 feet high. Now, we could label that 30 feet, but if we read the problem, we see this is measuring the height of the lantern, and the height of the lantern is not static, right? It's changing because it's falling. So we're not going to label it 30. Instead, we're going to label it with the equation for the lantern at a certain time, right? Which that equation will be 30, because that's the height of the lantern at the start, minus 16t squared. 16t squared, right? Then we're almost done, but we're missing one part of the drawing. We're missing the shadow. Now we have to be, okay, where would the shadow be? Well, if the light source is from here, the shadow is going to be behind the person, and we will label the shadow X, okay? Now we have to think about, what are we really trying to solve for in this scenario? Well, we're trying to find the rate of change of the shadow when t equals 1. So if the shadow is x, we are looking for dx over dt when t equals 1. And this will equal some value. And that's what we're looking for. All right? So then we can complete this drawing by turning this into a right triangle. All right? We have a right angle right there. So then what we're going to do is we're going to use proportions, right? Or this is a way I like to think about it, because my geometry is not too great, right? But say we split it into two different parts, right? So say we split it into this part where we just have the small triangle, right? With the x and the 6, so this part right here. And then we have the larger entire triangle where we have a x plus 10 on the bottom, and we have, actually we'll label this h, okay? We'll label this h just for our convenience for now, h. And this angle right here, which we'll call theta, is the same for both triangles. So we want to find some sort of way to relate opposite and adjacent, right? Well, we know we can take tangent of theta. So in this case, tan of theta equals opposite 6 over adjacent x, and in our case over here, tan theta equals, well, opposite h over x plus 10, right? So then we can equate these two, right? Because if these are the same tan theta, if they both equal this, we can equate them. So then let's move this over here. So we have 6 over x equals h over x plus 10. And let's recall, what are we trying to solve for? Well, we're trying to solve for the rate of change of x when t equals 1, right? So what we want to do is try to isolate x. So let's start with cross multiplying. And we get 6x plus 60 equals hx. Then we subtract hx and subtract 60 from each side, and we get 6x minus hx equals negative 60. Right? Then, or actually here, we'll just subtract 6x. So we get hx minus 6x equals 60, right? And then we divide, or we can factor out x, and we get h minus 6 equals 60. So then, what we do here is just divide by h minus 6, and we get x equals 60 over h minus x. Then from there, well, we already know h equals this. So this equals, well, 60 over 30 minus 16t squared. Yeah, 16t squared minus 6. Yeah. So then that equals 60 over 24 minus 16t squared, right? And that's x equals that. So now all we have to do is differentiate this and solve for x. Or sorry, plug in t equals 1, right? So then we get dx over dt equals, well, just use the quotient rule. If you take well, let's start with squaring the denominator, 24 minus 16t squared, and then this, right, we take the derivative of the numerator and multiply it by the denominator, but the derivative of the numerator is just 0, so 0 minus, then we take 60 and we multiply it by the derivative of this. Well, the derivative of this will be negative 32. Negative 32t. Okay? Then we can dx over dt equals, well, we multiply this together, and here, actually we'll just leave it like this. 60, the negatives will cancel out. 32t over 24 minus 16t squared. This whole thing will be squared. If we plug in t equals 1 and we did this math, we would end up with dx over dt when t equals 1 equals 30. And that's our answer for this problem, okay? So now, hopefully you understood that. Let's do one more problem. I'll be back. All right, so here we have our next problem. So the TV camera is positioned 4,000 feet from the base of a rocket launching pad. The rocket is rising at a rate of 600 feet per second. The angle of elevation of the camera is changing to keep the rocket in sight. Find the rate at which the angle of elevation is changing at the instant the rocket is 3,000 feet in the air. All right, so once again, we want to begin with a drawing. So let's recall, so we have a base, right, which is 4,000 feet away from rocket pad. So over here, we'll draw this, and 4,000, right? 4,000 feet away. And then we have our rocket over here. And our rocket is rising, right? And our rocket, once again, is not static, right? It's rising. So we're going to call it x. This is our x value, right? And then we're going to turn this into a right triangle. And we have our theta over here. This is our angle of our camera, all right? So then let's identify what are we actually trying to solve for. Well, we're trying to find d theta, because they're trying to find the rate of change of the angle of the camera, right, with d theta over dt, when x, or our height of the rocket, right, is 3,000 feet. So x equals 3,000, all right, and that's what we're trying to solve for. So then, just like last time, what we want to begin with is trying to find some sort of equation that will relate both x and theta, right? So, I'm sorry, no, but with the x, we want basically, let me restate this. So you might be tempted to try to fill in everything from here. You might say, okay, well, we're looking for when this is 3,000, all right, and this is a 4, 3, so this is going to be a 5, 3, 4, 5 triangle, all right? That's what you might be tempted to do, but you don't want to do that. You're going to give yourself extra information, and you're going to confuse yourself. Eventually, we will want to do that, but not yet. We're just trying to find some sort of thing we can do to relate everything we have here. Well, it just so happens that that would be tangent, because we have opposite and adjacent, and we have our theta. So tangent of, actually, let me write it over here. Tangent of theta equals, well, opposite x over 4,000, right? So then, actually, which also equals 1 over 4,000 times x. All right, that'll make it a little easier. Then, just like last time, after we have this equation, what do we want to do? We want to differentiate it, right? So we start with differentiating tan theta, and we're differentiating with respect to time, right? So tan theta, right, that will be secant squared theta, but we're differentiating with respect to time, so we have d theta over dt equals, right, well, we take the derivative of this, right, and we get 1 over 4,000, but then we're taking it with respect to time, so times dx over dt. Now, it might seem like everything's going wrong here. We have dx over dt, right? How do we really work with that? Well, if we look back into our problem, we can see the rocket is rising at a rate of 6,000 feet, right? So, this is our rocket, so we know dx over dt equals, sorry, not 6,000, that's 600 feet, right? So then we're almost done, but we have an issue, the secant squared theta, right? We just want to isolate d theta over dt. So let's multiply each, or divide each side by secant squared theta, which is the same thing as multiplying both sides by cosine squared theta. So we get d theta over dt equals 1 over 4,000 times, let's substitute in dx over dt now, 600 times cosine squared theta, okay? Now, we want to figure out what cosine squared theta might be. And this is when we go back to our drawing over here, and we say, okay, well, this is 3,000, and this is 4,000, so this must be 5,000, right? And we're looking for cosine theta, or cosine squared theta, and cosine theta is adjacent over hypotenuse, so we get cosine theta equals 4,000 over 5,000, which also just equals 4 over 5, right? So then cosine squared theta equals 4 over 5 squared, which is 16 over 25. So then we get d theta over dt equals 1 over, 600 over 4,000 times 16 over 25. Now, if you do this math, you will get approximately, let me see, what is it? 0.096, right? And this is in radians. So we know our angle is increasing at the rate of 0.096 radians per second. And that is the answer to our problem. Thank you for watching. Let me know if there's anything wrong or if you have anything additional to add. Have a great day.